Okay, so have you ever been in that situation where you know the physics, you've revised it, but you still somehow drop marks in the exam? It's so frustrating, right? Well, today, we are going to fix that. We're going to take a real exam question apart, piece by piece, to show you exactly how to lock in every single one of those marks. The secret is all about learning to think like the examiner. It's not just about getting the right answer, no. It's about hunting for the exact phrases, the precise wording that they are looking for to give you full marks. And that's exactly what I'm going to show you how to do. All right, section 1, setting the scene. First things first, let's get our bearings. We are diving into question 7 from a recent AQA GCSE Physics higher tier paper. And trust me, this is the kind of question that pops up all the time. So here's the setup. We've got a student trying to measure the volume and density of a metal ring, and they're using a measuring cylinder and a balance. I mean, this is a classic practical skills question, right? It's really designed to check if you understand measurement and, maybe more importantly, experimental errors. So let's see how they've structured this to award or take away the marks. Okay, on to section 2, the first 3 marks. Now, let's start digging into the first few questions. These are all about your knowledge of experimental errors. Think of these as quick, easy points, low-hanging fruit, if you know your definitions. Nailing these early on is a great way to build up your confidence for the trickier stuff later. So, question 7.1. First up, a multiple-choice question. It's asking what type of error you'd get if your eye wasn't in line with the water level. This is a classic, textbook example of parallax error, right? So the options they give are random error, systematic error, and zero error. What do you think? Which one is it? And the mark scheme answer is random error. But why? Well, think about it. Parallax error is totally unpredictable. One measurement, your eye might be a little too high. The next time, it could be a bit too low. The readings are going to jump around the true value. And that, my friends, is the very definition of a random error. All right, question 7.2. This is one of those one-mark questions that seems super simple, but your wording is absolutely key. The question is asking why the student should have used a thin string instead of a thick one. I mean, it seems kind of obvious, right? But how do you phrase that in a way that the examiner is going to tick? So the mark scheme actually gives 2 acceptable answers here. You could say that a thin string would affect the volume measurement less than a thick string, or you could say that a thin string would displace less water. See how they're basically the same idea? Both answers show that you get the core physics principle here. The string itself takes up space, it has volume, and that's an unwanted variable. A good scientist is always trying to minimize stuff like that. Okay, moving on to 7.3. Now this one's a little bit of a curveball. The true volume of the ring was 0.44 centimeters cubed. So why couldn't the measuring cylinder give an accurate value? Notice this isn't about the student making a mistake. This is about the limitations of the equipment. Let's dig into what that means. And here are the answers from the mark scheme. This perfectly highlights the concept of resolution. You see, the resolution is the smallest change an instrument can actually detect. And in this case, the markings on the measuring cylinder just aren't fine enough to measure to 2 decimal places, which is what you'd need for 0.44. So you could say that, or you could state the resolution is 0.2 or even 0.1 centimeters cubed. The point is, the tool isn't precise enough for the job. Any of these answers would get you the mark. All right, section 3, correction and calculation. Now we're getting into the big mark section. This is where precision, both in your method and in your number crunching, is absolutely critical. If you can nail this part, you are well on your way to a top grade. Okay, question 7.4. After the ring was taken off the balance, it still read 0.02 grams. So how could the student figure out the correct mass? Ding, ding, ding. This is a classic zero error problem. The balance isn't starting at 0, so every single measurement is off by a fixed amount. So what's the simple 1-mark solution? So the balance is showing 0.02 grams when it should be showing 0. The fix? You just subtract 0.02 grams from the measured value. Now, this is a classic examiner's trap. You can't just say, press the 0 button or recalibrate it, because the question implies you've already got the faulty reading. The only way to get the mark is to explain how to correct the data you already have. It's all about working with the numbers in front of you. And here we go, the 4-marker. Question 7.5, calculate the mass of the ring in kilograms. Okay, deep breath. This is where a lot of students can trip up and lose marks if they're not super careful. It's a multi-step calculation, and you better believe there's a classic trap hidden in there. Let's break it down step by step. First, let's see what information they've given us. We have the density, 21,500 kilograms per meter cubed, and we have the volume, 0.44 centimeters cubed. And stop. Right there. A massive red flag should be going up. Do you see it? The units. Kilograms per meter cubed for density, but centimeters cubed for volume. That is not a mistake. That's a deliberate trap. And spotting that is your first job. So the absolute first, most crucial step is to convert that volume. We have to get from cubic centimeters to cubic meters. You have to get this right. Just doing this conversion correctly gets you 1 full mark. Honestly, this is the #1 place people make a mistake, so please, please, please always check your units before you even think about picking up your calculator. Okay, step 2. Now that our units match, we can move on to substitution. You just take the density formula and plug in the numbers you have. So 21,500 equals mass divided by our new volume in meters cubed. And listen to this, just writing that down, just showing that substitution is enough to get you the second mark. You're showing the examiner your thought process, and they love that. Right, step 3 is to rearrange the formula. We need to solve for mass, so we need to get mass all by itself on one side of the equation. A simple bit of algebra does the trick. And again, this is a separate mark. Just showing that you can correctly rearrange the formula gets you mark number 3. It proves you know how to handle the equation. And finally, you punch those numbers into your calculator, and you get the final answer, 0.00946 kilograms. The mark scheme also says that standard form, so 9.46 times 10 to the minus 3, is perfectly fine too. Getting that number is your 4th and final mark. And there you have it, a perfectly executed 4-mark question. So let's step back for a second. Section 4, your key takeaways. What have we actually learned from taking this one question apart? It's about more than just knowing the physics, isn't it? It's about having a solid exam strategy. So let's boil it all down. If you want to think like an examiner, you've got to nail these key points. First, know the difference between random, systematic, and zero errors. Second, always think about the limitations of your equipment, the resolution. Third, and I can't say this enough, watch your units. That unit conversion is such a common trap. Fourth, show every single step of your calculation. And finally, when you can, try to use the exact wording you might find in a mark scheme. If you can master these things, you'll be unlocking top marks, not just in physics, but in any science exam. See? By applying these principles, by really thinking about what the mark scheme is looking for, you can turn a question that looks pretty challenging into a real opportunity to show what you know. So, now you know how to get full marks on this question. Which one are you going to master next?